Hello and welcome back for another VMK in the C++ series. In this VMK, I'll be describing bit fields. So let's jump into Photoshop and let me draw some diagrams to show you what bit fields are. A bit field is really a chunk of memory that is broken up in such a way so that you can access the individual parts of that memory block. Now typically, memory in C++ has different sizes. You can have a variable that is of a type char, you can have a variable that's of a type short, you can have integers, you can have longs, you can have floats, and all those. I'm not going to be talking about floating point numbers, we'll just be talking about integer values. A char is actually 1 byte of memory, and 1 byte happens to be 8 bits. So if I were to say I want 1 byte of memory, then in my memory space here, I would have 8 individual bits that I can toggle however I want. As I assign different values to this character, I'll be setting these bits 1, 0, 0, 1, however I want to represent that value. A short is 2 bytes, defined in C++, which means we have 16 bits to play with. And a long and a integer both happen to be 4 bytes. On different platforms, like for instance if you're programming in Java, an integer would be 4 bytes and a long would be 8 bytes, I believe. So you have to be careful when you're crossing different platforms because an int may be defined differently than a long and vice versa. But in Windows under C++, a int and a long are basically the same thing, and they both are 4 bytes. And 4 bytes happens to correspond to 32 bits that you can play with. So bit fields, what they do is they let you address into a specific bit inside of a chunk of memory. So with a character, you've got 1 byte, so 8 bits to play with, but you can further break that down into smaller chunks so that you can access them individually. So I could say these 8 bits I want the first 2 to be called one thing, then I want the next 4 to be called something else, and then the remaining 2 I want to call that something else. So in total here we have 8, and all of these 3 different things could be stored inside of this 1 byte. So that's what bit fields are useful for. So let's go into C++ and take a look at how we can play around with bit fields, and I can point out some downfalls of bit fields as well when you start mixing up data types. I'm going to start off by creating a new project. I'll just create a Win32 console application and I'll call it bitfields. Hit OK, and the default application settings here should be fine for us, so hit finish and I'll create our project. So to start off, I'm going to create a function which displays a binary number so we can see all the different bits for all the different possibilities that we can store inside of 1 byte. Now going back into here, I said that 1 byte is equal to 8 bits, and if we have 8 bits of data to encode, that means we have 2 to the 8 values that we could store inside of that, which means we can have a total of 256 different numbers that can be saved inside of 8 bits. So going back into here, you can see I create a for loop that goes from 0 all the way up to 256, and each time I'm just going to print the number that we're currently at, and then I'm going to call this function called show 1 byte binary number. What that's going to do is take in the value here that I'm currently at, and it's going to print out the binary representation of that number to the screen so that we can see what all the numbers look like. So let's go and implement this show 1 byte binary number function call. What this does is we're passing in a character value. So this is a 1 byte number, and we're going to go through a for loop here, and for each time we're going to check to see whether the current value that we're at is masked at the current value inside of this 1 byte value. So we can do a bitwise operation here. Notice that this is not a double ampersand, it's a single one. So in other words, what this is doing is checking to see if the current bit at this value is high, and if it is, then it's going to return true, so that means we're going to display a 1. Otherwise, we're going to display a 0, and then we just continually loop through here for every single high value inside of that bit array. So what's going on here is we have our 8 bits. Let me draw them out this way. 1, 2, 3, 4, 5, 6, 7, and 8. So this one here is 1, this is 2, this is 4, 8, 16, 32, 64, and 128. So I'm going to start at the value of 128, so that's going to be a representation of 1, 0, 0, 0, 0, 0, 0, 0. That's the value of 128 stored in 1 byte. And I'm checking to see if whether our value, whatever it is that we passed in there, ANDed with this value here is equal to true. It's only going to be equal to true if the highest bit in this value is also a 1. That's the only way that this operation here can return true. So if that's the case, we're going to display a 1. Otherwise, we're going to display a 0. Then the next iteration to that loop takes the current value of I and shifts it over by 1. So in other words, what's going to happen is on the second iteration to that loop, instead of having 1 there, we're going to have the 1 located here. So now we're going to be checking to see whether our value is ANDed with the value of 64. And that's going to be checking the second location. The next time we're going to be checking for 32. So we have this value here stored in the thing, and we just continue all the way down until we have 1 located at the very end and zeros everywhere else. So that's basically how this code here works. We're just shifting that 1 all the way down through that entire 8 bits, and every time we hit a 1, we display a 1, and if we hit a 0, we display a 0. So if we go and press Control F5 on the keyboard, we'll build and run the code, and now we can see all the binary representation values for all the 256 values. So 0 is 0 all the way across, 1 is going to have a 1 down here, 2 would have 2, 3 would have 1, 1, 4 is 1, 0, 0, and so on. So you can see that there's a binary pattern here. If you're interested in the details of how binary and regular decimal numbers are represented, I have a separate VMK in the C++ series early on that describe the representations here and how you can convert one from another. But that's not what we're interested in. What we're interested in is taking a look at these different kinds of representations. So you need to be aware of how numbers are structured inside of a bit array. So you can use this as a reference for later on in this VMK when I'm comparing different numbers. If you get a little bit confused on what's going on, run this through, take a look at the way that the bits are structured, and then you should be able to figure out what's going on. So that's just a little handy function I wrote for you guys. Now there's one other thing I wanted to describe before we head on down into the bit field section, and that's the sizes of variables. So in Photoshop there I showed you that a character is 1 byte, a short is 2 bytes, and an integer and a long are 4 bytes. But just to prove it here, here's a chunk of code that will basically demonstrate the exact same results. So all I'm doing here is I'm taking the character, I'm calling the size of function, and it's going to return to us how many bytes a character is. And I'm going to save that here so we'll see it. Then 1 byte is equal to 8 bits, so I'm just going to take that same thing, multiply it by 8, and then display it to the screen so we can see how many bits it is. And then finally, I'm going to take the unsigned character value of -1 and print that out to the screen so we can see what is the actual maximum value that can be stored inside of that structure. So in here, how much can we store in 1 byte, how much we can store in 2 bytes, and so on. So if we were to run this code, 1 character is 1 byte, which is 8 bits. Therefore, the maximum value has to be 255 characters. 2 bytes is 16 bits, which gives us a maximum value of 65535. And then an integer and a long are both 4 bytes, which are 32 bits, which give us this maximum value here that we can represent. So just to confirm that I'm not lying when I say that integers and longs are the same in C++. You can confirm that on your own compiler by running the exact same code. So now let's take a look at bit fields. How is it that you define a bit field inside C++, and how is it that we can use them? I'm going to comment this code out here as well since we won't be needing it. Well, a bit field is defined inside of a structure. So typically you'd do something like this, struct, and you'd give the struct a name, so I'll call it bit field. And you would give yourself some sort of member variable. So here I'm going to say unsigned character A, and then if I wanted to use that, down here we would go bit field like this. So that's going to give me some memory of type bit field, and then if I wanted to assign a value to that bit field, then we just use the regular operation, and let's say I wanted to set that equal to a value of 10, then that's the way we would do it. So doing it this way, what we're doing is we're saying, okay, this bit field is going to have a variable called A, it's going to be of size character, and I'm just storing 10 inside of it. But this is using the entire 8 bits of this character variable, so we're not actually individually marking different access points inside of that bit field. If we did want to do that, we need to use the colon operator and pass in how many bits we want this variable to represent. So if we don't specify anything here, then we basically do this. Our A variable will use all 8 bits because a character has 8 bits to work with. So here, this is exactly the same thing as if we were to do this. However, what we can do is change this up to use something less than 8. Let's say I wanted to use 4. So if I do that, then our character here now is going to be able to access only 4 bits within our full 8-bit array. How is it that we get at the other ones? Well, we can declare another variable, let's say b here, and this one I can set to be 3, and now the first one I can have 4 bits of values that can be stored there, and in the second one I can only have 3 bits of data that can get stored inside of there. So that's the general syntax that you use when you use bit fields. One thing that you do have to be careful with is that when you do specify how many bits you want to use for each of your variables, that you don't exceed the maximum number of bits that can be stored in that data type. So we've seen a character can only have 8 bits. So if I were to define this as having a value of 10, then when we try to compile this code, you'll get an error message saying that this bit field type is too small for the number of bits. So that's basically telling you we don't have 10 bits inside of a character to work with, so we need to decrease this down. We could go as high as 8, but no higher than that for a character array, since that's how many maximum bits we have to play with. If we compile that, you notice that that succeeds successfully. Now let's play around with this for a little bit. Let me create a bit field structure like so, where we have 3 values, A, B, and C. And down here, what I'm going to do is I'm going to declare some memory called bit field, and then I want to print out how much memory this bit field actually uses. We can do that by using the size of operator, and we're just going to pass that into here. So if we run this, we can see that this bit field has 3 bytes because we are storing 3 unsigned character values inside of that structure. However, if I were to change this so that this one uses 3 bits, this one uses 4 bits, and let's say this one uses 5 bits. Now if I run the code, notice that we're only using 2 bytes. So we still have 3 variables here, but we're only using 2 bytes. And the reason why we're using 2 bytes as opposed to 3 bytes is because all of these get packed up together. So the A value here is using 3 bytes. Then right beside it, we have the B variable, which is using 4 bytes. So total here is 7 bits, and 7 bits will fit inside of 1 byte. Then we have C, which is another 5 bytes. So in total, we have 12 bytes, and 12 bytes doesn't fit in 1 character, so we need 2 characters strung together, which gives us our 2-byte length. So now you can start seeing how bit fields might become useful. So now let's start saving some values inside of this bit field. I'm going to create a for loop here, where I'm going to start off my value here as a value of 3, and I'm going to continually increment this by multiplying it by 2, and each time through, we're going to be saving the current value of I into each of those bit fields. And finally, we're going to be printing out the results. So the I value is going to get printed, and then we're going to show what is the current value for A, what is the current value for B, and what is the current value for C. And all of those are going to be represented using the same function that we used at the very beginning to represent the values as binary values so we can see the bits individually. So let's run this code and take a look at the output. Okay, so we start off with the value of 3. Then we multiply by 2, so we have 6. We multiply by 2, we get 12, then 24, 48, and then 96. So each of those in binary representation are shown here. We have 1, 1, then we have 1, 1, 0, 1, 1, 0, 0, and so on and so forth. Those two high bits across every time we multiply by 2. And for the A value, we store 3 the first time. We're storing 6 the second time. And notice that the third time, we're storing 4. And then we have 0, 0, and 0. Over here, we're storing 3, we're storing 6, we're storing 12, and then we're storing 8. And then we have 0 and 0. And finally, over here, we're storing 3, 6, 12, 24, we're storing 16, and then we have 0. So what's happening is because our bit field is defined as having a maximum, either 3, 4, or 5, we cannot store a number larger than will fit inside of that bit field. So notice that here we only have 3 bits to work with, but the value that we're trying to store in it is actually 4 bits because we have 1, 1, 0, 0. So we can't store that inside of 3 bits, so what happens is we actually truncate that first bit and we only store the remaining thing. So that's why we only have the value of 4 stored here inside of the value of A, as opposed to the value of 12. So it is something to be careful of when you are trying to cram numbers inside of a bit field where the bit field is not large enough to store the value that you're trying to cram into it. And here we see we only have 4 bits to save values in, so here the top one gets truncated. Here we have 5 bits to play with, so the top one gets truncated here. And then finally, the last number is outside of the range of all of them, so that's why we have zeros all the way across the board. The other thing that you have to be very careful with when using bit fields is to make sure that you are using signed and unsigned values appropriately. So let's say I declared my variable a as being a signed character value as opposed to an unsigned value. If I do that and I'm specifying it to only have 3 bits, then let's take a look at the output if I were to do the following. So inside of this chunk of code, I'm going to loop through 8 times. Each time, I'm going to be saving the current value inside of the bit field. And I'll be displaying the results here to the screen. So the current value that we're saving inside of the bit field, the value that represented as a binary value, and then the actual value stored inside of the A inside of the bit field, and then also what is the value stored inside of the bit field as a decimal, as opposed to as a binary number. So let's run this and take a look at the output. Notice here that the values range from 0 to 7, so that's the loop that we're going through, and that's what we're trying to cram into 3 bits inside of our signed bit field. Well, 3 bits are only those last two bits there that we can play with. So initially 0 is 0, which means we're saving 0. 1 is stored correctly, 2 is stored correctly, 3 is stored correctly, but notice what happens with 4. 4 triggers the highest bit here, which happens to be the signed bit, because we've defined our bit field to use a signed value. Well, as soon as that highest bit gets triggered, that tells our code that that is actually a negative number, and a negative number with 2 zeros beside it is a representation for -4, not for the value of 4. Moving on, we have 1, 0, 0. So 1, 0, 0 is the representation for -3. Then we have -2 and -1. So we can see, even though we're trying to cram in the value of 6, which is 1, 1, 0, inside of our 3-bit bit field, which is signed, we're actually going to be storing a value of -2. So if you do get wonky behavior and you're not quite sure why you're plugging in one value into your bit field, which is clearly able to fit inside of 3 bits, be aware that there is a big difference between a signed bit field and an unsigned bit field. Typically, I only use unsigned bit fields because they're easier to manipulate, but if you are trying to store actual number representations inside of there, then using signed bit fields does make sense. Now let's take a closer look at how bit fields are packed inside of the structure. I'm going to comment this out and go back to what I had up above here. So we're defining a bit field as, let's say, 3 unsigned characters. And we've already seen that when we run this, we get 2 bytes of data used up to represent this bit field. I'm going to comment this out, and instead, let's declare our bit field so that instead of using a unsigned character, unsigned character, unsigned character, let's do the last one as being an unsigned short. So it's still 3, 4, and 5. All I'm doing is I'm changing the data type here. What would you expect the number of bytes to be for this bit field here? Did you say 2? Did you say 3? Well, if you said either 2 or 3, you'd be wrong. It's actually 4. The way that C++ is packing this bit fields is it's taking the largest data type and trying to match everything to that largest data type. So it can see that it can take this character and this character here, pack them together and store that inside of 1 byte because it's 7 as opposed to 8, so they will fit. However, it can't align that with this short, which is 2 bytes. So instead, it has to shift this around and give this representation here 2 bytes, and then this value for C is in the extra 2 bytes, so in total, this is going to be 4 bytes. Now let's take a look at another example. What do you suppose you'll get if we're to pack our bits, let's say this way? Guesses? Anyone? Well, if you said 6, you would have been correct. What's happening is, once again, it's taking the character here, aligning it with the largest, which is 2 bytes. So this one here now takes up 2 bytes. Even though we only need 3 bits of those 2 bytes, we are still going to be allocated an entire 16 bits to use for this representation of A. This short here is going to be 2 bytes as well because it's a short. And this C here is going to also be 2 bytes because it needs to line up with this short. So in total, this one here is going to be 6 bytes. So you can see the way that you define your structure really greatly affects the amount of memory you're going to be using. So always be thoughtful in terms of how you order your variables inside of your structures so that you pack everything together that is of similar types so that the compiler can compress the bits into the smallest possible memory space that it can. And for this example you saw, it's best to use all unsigned characters because all of these values 3, 4, and 5 will fit inside of a character which has a maximum of 8. So there's no point in using something larger because it's going to just bump everything up to something that's not really required. Now what you could do is you could make everything a short. I'll just take this one up here and copy it down below. And if we do short A, short B, and short C, what do you expect to see? Well, the result is 2 bytes once again. Even though a short is 2 bytes, the next one is 2 bytes, but because they're the same data type, the compiler can squeeze those two together to be side by side. So therefore, these 3 bits are right beside these 4 bits, which are next to these 5 bits, and all of those happen to fit inside of 2 bytes. So that's exactly how much memory your bit field will take up. The other thing that I want to point out here is the order in which you stack these bits represent how the memory is going to get stacked inside of your bit array. This is actually telling the compiler that in memory, this is going to be adjacent to this, which will be adjacent to this. Let me introduce a few more structures with the same bit field variables, but just reordered into all the different permutations that are possible. If we take a look at this code here, what I've done is I've created a constructor where I'm going to initialize the A, B, and C values to be equal to 1, 2, and 5. And all of these are within the valid range of each of these bit fields. Then what I've done is I've created bit field number 2, which also has A, B, and C, but now they're ordered in a different way. So A is still Oh, I actually changed the number of bits here. So A should have 2 bits, B should have 2 bits, and C should have 3 bits. I did that specifically because 3 plus 2 is 5 plus 2 is 7, which fits all inside of 1 byte. So we can work all inside of 1 byte, and we can do a very easy comparison here. So all of these still fit inside of these values. So 1 will fit inside of 2 bits, 2 will fit inside of 2 bits, and the value of 5 will fit inside of 3 bits. So this bit field here is defined with ABC. This bit field number 2 is defined ACB. We have BAC, we have BCA, CAB, and finally CBA. So all the different permutations of those 3 variables we have, and for all of them you'll notice that the constructor constructs the value of A to a value of 1, B to a value of 2, and C to a value of 5. So all of those you can see are exactly the same. Now, down below here, let me display to the screen how each of those bits are stored inside of memory. First, I'll display to the screen that A has 2 bits, and the value is whatever's in the first one. B is 2 bits as well, and it's the value of B. And C has 3 bits, and it should display that we have 5 there. Then we have the representation for ABC, representation for ACB, for BAC, BCA, CAB, and CBA. For each of those, I'm going to take the bit field, cast it over to a character, and then take the value of it so that we can pass it into our function to show the actual binary representation of those bit fields. So let's run this and take a look at the output. So we know that the value of A is always 0, 1, because that's the value of 1. For the value of B, we're always storing 2, which is 1, 0. And for the value of C, we're always storing 5, which is 1, 0, 1. If we have A, B, C, we can see that we have, well, the topmost here doesn't matter what that value. It could be 1, could be 0, depending on how the memory was initialized originally. We're not actually using that bit for anything, because 2 plus 2 is 4 plus 3 is 7, so we're only using the bottom 7 bits of the 1 byte that we have stored inside of our bit field. Okay, so if we're storing ABC, well, A is right here at the very bottom, 0, 1. B is the next 2 bits, 1, 0, and C is 1, 0, 1. Then we can take a look at ACB. Well, A is still down here, 0, 1. Now we have C, which is 1, 0, 1, and B at the top here, which is 2, which is 1, 0. If we have BAC, well, B is 2, which is 1, 0 at the end. Next one is A, which is 0, 1, and then C, which is the last one, 1, 0, 1. We have BCA, so B is again 1, 0, C 1, 0, 1, and A is 0, 1. And we have CAB and CBA. So you can see we're actually stacking all of these bits side by side inside of our memory from bottom to top according to however many bits we have to play with. So this is the way that bit fields are stored in memory, and this is why you can compress your variables down to smaller chunk sizes as we saw here, and why we have to expand them out whenever you're changing things up based on different data types. The last thing that I'd like to demonstrate is how to use unions with bit fields. Now, I typically don't do this because you lose the ability to use constructors with your bit fields, but unions do sometimes come in handy if you do want to initialize your bit field all in one swipe. So let's do this. I'm going to comment out all that code and add in the following union. So notice here that I'm creating a union for my bit fields. I'll actually call it bit field union. And this guy is going to be a union between our bit field, which is this structure here, and a unsigned character. So we've seen here that all of these bits here stack together to be 1 byte, and 1 byte is the same representation as a unsigned character. So we can represent a bit field either as a bit field, or we can represent it as a unsigned character value. Now notice that the compiler is complaining here because it's saying, well, actually, let me comment out all this other code. And if we try to recompile, it's saying it cannot create this union because we have a user-defined constructor. So what that's basically saying is this bit field here has a constructor, so it doesn't know how to construct these two things together inside of the union. If I remove that constructor, then the squiggly disappears and the compiler has no problem now because it can represent these things also as a character. So let's see how we could use this union. Down inside of main, I can do the following. I can create a bitfield union variable here, so call it BF, and I can set the individual bitfield values using the bitfield values A, B, and C. So I'm going to set them to 1, 2, and 5, just as I did before. And we can print them to the screen using this code here. So A is going to be equal to A, B will show here, and C will show here. And finally, we can use the union to read all the bits in one go. So we can use the unsigned character representation of that same bit field and display the results this way. So this is going to stack them all together and display the results. And finally, because we now have a union, we can assign all three of these all in one go using the unsigned character value. So let's say I pass in a value of 38 into there. Well, 38 happens to be hex 26, and hex 26 represented as a binary number is 0010, that's the 2, and 0110, which is the 6, which if we take a look at our bit field definition, we saw that our bit field definition is A, B, and C stacked side by side. Therefore, A, which is 2 bytes, B, which is 2 bytes, and C, which is 3 bytes, means that we're going to have 2 bytes, 2 bytes, 3 bytes. So we can take these two, that's going to be A, these two, which is going to be B, and these three, which is end up going to be saved inside a C. And to confirm that, we can print out the results here to make sure that that's actually what we are getting. So let's run this code and take a look at the output. Our bit field here has our original values 1, 2, and 5, and then ABC, which is the value stored inside of the unsigned character value, is this value here, 1, which we don't care about, and then we have 101, which is 5, 10, which is 2, and 01, which is 1. And when we save that out to the unsigned character here, we basically can then take a look at the output and see that we are getting, truthfully, a value of 2, a value of 1, and a value of 2, just as we expected. So that's how you can use unions with bit fields to assign and read out values all in one go. However, I don't find this very handy because you have to be very careful not to be overwriting your bit fields in the wrong order if you happen to mess up the order of your A, B, and C inside of your structure. If someone was to come in, switch things up on you, all of a sudden this code would start doing things that you wouldn't be anticipating because things are shifted around in a different order. I find it a lot more helpful to have constructors inside of my bit fields and assign values directly to each of these named bits the way that I've defined them. Okay, so that's all I wanted to show about bit fields. I hope the video was helpful. If you have any questions about this VMK, head on down to the forums by clicking on the thread link beside the VMK and post your questions there.